We now start our discussion on the first module of chapter 4. In the undergraduate level, you have come across two kinds of convergences of sequences of functions. One is pointwise convergence and another is uniform convergence. Recall that a sequence of functions fn is said to converge to a function f pointwise if for every point x belonging to the domain, the sequence of values f n x converges to the value of f x, and f n is said to be convergent to f uniformly if for any epsilon greater than 0, there is a positive integer capital N such that for all x belonging to the domain, mod f n x minus f x is less than epsilon. Now, in this chapter, we will look into three kinds of convergences which are defined with the help of Lebesgue measure and which are more general than the notions of pointwise convergence or uniform convergence. So, in the first module, we start with the notion of almost everywhere convergence, which is a generalization of the notion of pointwise convergence. We start with the formal definition of pointwise convergence. A sequence of real valued functions f n defined on a subset of R is said to converge to a function f pointwise if for each x belonging to a and given epsilon greater than 0, there is a positive integer capital N which is dependent on both the point x and given epsilon such that mod f n x minus f x is less than epsilon for all n greater or equal to capital N. Now, we present the first kind of convergence which we are introducing. A sequence of real valued functions f n is said to converge to f almost everywhere. In short, we write f n tends to f a e if there exists a measurable set A with mu a equal to 0 such that the point sequence f n x, that is the sequence consisting of the values of f n at the point x, this sequence converges to f x for all x belonging to a complement. Let us consider an example. Define f n x as n when x is a rational number and 0 when x is an irrational number for all x belonging to closed 0 1. Take f as the constant function which takes the value 0 on the whole interval closed 0 1. So, see that at all irrational points, the values of f n and f are all equal and equal to 0, but at the rational points, the values of f n is a divergent sequence. So, it cannot converge to 0, but we already know that the set of rational numbers has Lebesgue measure 0. So, we can say that though this sequence f n does not converge to f pointwise, but f n converges to f everywhere except a set of measure 0. and so we can say that Fn converges to F almost everywhere. We now present the first results for almost everywhere convergence. The results deal with the limit function. Recall that when a function sequence Fn is pointwise convergent, the limit function is always unique. But when we consider this generalized notion of convergence, that is almost everywhere convergence, that statement is not necessarily true. So, we have the first result that if Fn converges to F almost everywhere and F equal to G almost everywhere, then Fn also converges to G almost everywhere. Secondly, if Fn converges to F almost everywhere and at the same time Fn converges to G almost everywhere, then the two limits F and G are related by the relation that F equal to G almost everywhere. Third result is that if Fn converges to F almost everywhere and if Fn is equal to Gn almost everywhere, then also Gn converges to F almost everywhere. Since the proofs of all the assertions are quite similar, we will present the proof of only the assertion 2. So, by our assumption, Fn is a sequence of functions which is almost everywhere convergent to the function f, as well as it is everywhere convergent to the function g. Then from the definition of almost everywhere convergence, we can find measurable sets A and B with mu A equal to mu B equal to 0, such that the sequence Fn x n belonging to capital N converges to f x for all x belonging to x minus a, since Fn converges to f almost everywhere, and at the same time the sequence Fn x n belonging to capital N converges to g x for all x belonging to x minus b. Now, see that if we consider the set A union B, then A union B is a measurable set and mu of A union B is also 0. And obviously, for all x belonging to A union B complement, we have f x is equal to limit n f n x, but this is again equal to g x. So, we have a set, namely A union B, whose measure is 0 and on whose complement we have f x equal to g x. So, f equal to g almost everywhere. We now consider the second definition, where we present another notion of generalized convergence with the help of Lebesgue measure. Now, whenever we have a notion of convergence, always there is a Cauchy condition related with the notion of convergence. So, when we have defined a notion of convergence almost everywhere, naturally we should expect a notion like Cauchy almost everywhere. Formally, a sequence of functions f n, n belonging to capital N, is said to be Cauchy almost everywhere if there exists a measurable set A with mu A equal to 0 such that the sequence f n x n belonging to capital N, this is a Cauchy sequence for all x belonging to A complement. Now, we know that in real analysis, when we talk about pointwise convergence, a sequence of functions f n is pointwise convergent to a function f if and only if it is Cauchy almost everywhere. Here we have this result. If f n converges to f almost everywhere, then the sequence f n is Cauchy almost everywhere. Conversely, if f n n belonging to capital N is Cauchy almost everywhere, then there exists a function f such that f n converges to f almost everywhere. And further, if each f n is assumed to be measurable, then we can choose the limit function f also as a measurable function. First, we consider the proof of assertion 1. So, by our assumption f n converges to f almost everywhere, then there exists a measurable set A with mu A equal to 0 such that on A complement, that is for all points x belonging to A complement, f n converges to f, that is f n x, the sequence converges to f x. But we know that a sequence of real numbers is convergent if and only if it is Cauchy. So, for all x belonging to A complement, the sequence f n x n belonging to capital N is a Cauchy sequence, and this shows that f n is a Cauchy almost everywhere. Conversely, if f n is Cauchy almost everywhere, then from our definition of almost everywhere concept, there exists a measurable set A with mu A equal to 0 such that the sequence f n x n belonging to capital N is a Cauchy sequence for all x belonging to A complement. And this means that for all x belonging to A complement, the sequence f n x being a Cauchy sequence is also convergent and it has a unique limit. So, let us define the function f in this way: f x equal to limit n f n x for all x belonging to A complement, and f takes any value on the set A where we do not know anything about the Cauchy condition. See that on A complement, of course, f n converges to f and the measure of the set A is 0. So, we can say that f n converges to f almost everywhere. Now, to get a measurable function as the limit, the trick is that we have to define f x equal to 0 for all x belonging to A. Define g n equal to f n into characteristic function of A complement. Now, see that since A is of measure 0 and A is consequently measurable, so A complement is also measurable. So, its characteristic function is also measurable and product of two measurable functions is again measurable. Thus, we have that each g n is measurable. Obviously, g n tends to f on the whole set X, because on that exceptional set A where we do not know anything about the convergence of f n, we have put the values of g n and f all 0. Now, we already know that the limit function of a pointwise convergent sequence of measurable functions is again measurable. So, here f being the limit of the sequence of measurable functions g n is measurable. Now, we define another type of generalized convergence, which is defined with help of Lebesgue measure. A sequence of real valued measurable functions f n is said to converge in measure to a measurable function f if for any epsilon greater than 0, limit n tends to infinity mu of collection of all x where mod f n x minus f x is greater or equal to epsilon is equal to 0. That is, what we are trying to do is that we are taking for any arbitrary epsilon greater than 0 those points x where the deviation from f n to f is greater or equal to epsilon, and we are saying that as n tends to infinity, this set becomes small and small in respect of measure. And in this case, we write f n converges to f in measure. We first examine the relation between this notion of convergence, that is convergence in measure, with convergence of the values of f n x to a definite value f x. For this, let us consider this example. We first take closed interval 0 1, call it E 1, then we divide the interval into two disjoint parts, closed 0 half open, call it E 2, and closed half 1 closed, call it E 3. Then we divide the closed interval 0 1 into three disjoint equal parts, 0 to 1 by 3, 1 by 3 to 2 by 3 and 2 by 3 to 1. Now, see that if we consider the intervals in this way, then we have a sequence of intervals E n such that the measure of the first interval is 1, then the measures of two intervals are half, then the measures of 3 intervals are 1/3. So, I have a decreasing sequence of real numbers. So, the sequence mu E n is a decreasing sequence of real numbers which converges to 0. Now, let us define f n as the characteristic function of E n for each n. Now, since each E n is an interval and so is measurable, so f n being the characteristic function of a measurable set is also measurable. Now, consider the constant function 0, that is we take the function f which takes the value 0 on the whole interval. First observe that the sequence of functions f n converges to f in measure. Why? Because if we take any arbitrary epsilon where 0 less than epsilon less than 1, then if we consider the collection of all those points x belonging to closed 0 1, where mod f n x minus f x is greater or equal to epsilon, this set is nothing but the set E n, and so mu of collection of all x where mod f n x minus f x is greater or equal to epsilon, this is equal to mu E n, and this tends to 0 as n tends to infinity. So, I have a sequence of measurable functions f n which converges to the constant function 0 in measure. Now, we want to know whether this sequence of functions converges at any point pointwise. For that, let us take any arbitrary number x from closed 0 1. Now, see that f 1 x equal to 1, since E 2 and E 3 are disjoint and E 2 union E 3 is equal to closed 0 1. So, the point x can belong to at most one of the two sets, and consequently either f 2 x will be equal to 1 and f 3 x will be 0, or f 2 x will be 0 and f 3 x will be equal to 1. Similarly, in the next 3 terms of the sequence f n x, we will have 2 zeros and 1 1. And so, if we proceed in this way, we see that the sequence f n x is a sequence consisting of zeros and ones which contains infinitely many zeros as well as infinitely many ones, and so it cannot be convergent to any real number. So, there is this example of sequences of functions which is convergent in measure, but it is not convergent pointwise at any point of the domain. We now present a result on the limit function of the convergence in measure. The result states that if f n converges to f in measure and f is equal to g almost everywhere, then f n converges to g in measure where g is also measurable. The proof goes like this: since f is equal to g almost everywhere, so there exists a measurable set A with mu a equal to 0 such that on A complement f is equal to g. Let epsilon greater than 0 be given. Now, collection of all x where mod fn x minus gx is greater or equal to epsilon, this is subset of collection of all x where mod fn x minus fx is greater or equal to epsilon union A. And consequently, measure of the set x where mod fn x minus gx is greater or equal to epsilon is less or equal to mu of x where mod fn x minus fx is greater or equal to epsilon plus mu A, and see that mu A is equal to 0, and as fn converges to f in measure. So, the number in the first part of the right hand side also tends to 0 as n tends to infinity, that is limit n mu of x mod fn x minus gx greater or equal to epsilon, this also becomes 0, and consequently we have our desired result. So, to summarize, what we did in the first module of chapter 4 is that we have defined two generalized notions of convergence. First, we defined the notion of almost everywhere convergence, and then we have defined the notion of convergence in measure. We have seen the basic properties of convergence almost everywhere, and we have finished the module with one result on the limit function of a sequence of functions which is convergent in measure. And with this we end this module.